This is Lecture 9E on the motion of sailboats and on coasting problems. Talking about here, here's the water, here's a boat with a sail in it, and we have the wind blowing on it, and that provides the force due to the wind, but there's a resistive force here in the water, and the faster we go, the more it resists us, and that's why we use this model. So we're choosing the model F equals minus k times v. The resistive force is proportional to the velocity. As before, this is a separable equation. It could also be solved by an integrating factor. It is exactly the same as the first example we did above when we were looking for terminal velocity. So I'm going to solve it in the same way just so you get used to it. First thing I do is put it in standard form. Remember, to use an integrating factor, you put it in this form. dy by, I'll say dt, plus a y equals b, and a and b can depend on time. In this case, a is k over m. We just rearranged the equation to get this. There was no big deal here. And here's the force due to the wind divided by the mass of the sailboat. Using a equal to k over m, we develop our integrating factor, which is e to net. Why do I always want to put a negative up there? So I'm going to erase that. Equals e to the integral of a dt. A is a constant. The result of that integration is just k over m times t, and that's what's written here. Then the solution, after we do several gyrations, is y equals e to the negative integral of a dt times the integral of e integrating a dt times b dt. Okay. Here's the B. The B was the force due to the wind, should have had a subscript on it, divided by mass. Okay. That's B. Already pulled the mass out from underneath the integral sign. And now here's the integrating factor right here, multiplying it. Here's our integrating factor right here. And here it's with a negative sign. Let's say that the force due to the wind is a constant, so I can pull it out from under the integral sign, and all I'm left with is the integral of e to the k over m t dt, okay, and that's m over k e to the k over mt plus some constant c. All right, and that's what you see right here. That's an easy exponential to integrate. Now distribute through this leading term, and here's the result. The velocity equals the force due to the wind divided by k plus some constant c times a decaying exponential. Looks familiar, right? The form should look familiar. Let's let v naught be the velocity of the sailboat right before the wind picked up. We can then use that to evaluate the constant of integration in our solution, and here's the result. This result should look very familiar. These results should start to look, should be able to pick out various terms in them right away. Okay, the first term we have here does not depend on time. The second term here is some values multiplied by a decaying exponential. That decaying exponential term is your transient solution. F over k is the steady state solution, or the equilibrium solution. This is the one that the velocity approaches. So here's a graph of one of the solution with some numbers applied to it. So the mass of the sailboat is going to be 1,100 kilograms. And it had a velocity of 1 meter per second when suddenly a wind that supplied 50 newtons of force came up and started pushing. The resistance of the water, let's say K is 5. That's not an unusual number. So the resistive water is proportional to the velocity, and the constant of proportionality has a value 5. So from this we can work out the steady state solution would be 10 meters per second. All right, and you can see what we've got here. This is our equilibrium steady state solution, see. So we have an equilibrium or steady state value right here, and that's F over K. That was that leading term. Then we started here. This was our initial velocity of 1, and there was a decaying exponential. So the velocity can't jump right up here to F of K as soon as the wind hits it. Instead, it follows this path, and it asymptotically approaches the equilibrium value or steady state value of F over K. Okay, let's do one more problem, and that'd be a coasting problem. This only applies to objects moving on the ground, since you're not going to coast as you're falling. You will fall till you reach that, as you approach that terminal velocity. In this coasting problem, only resistive forces act on the object. This is though you had some velocity, and then you just some initial force that got you going, and then that force stopped. So if there's no force on this object, and it starts with some velocity v, the velocity should decrease to 0. But how does it do it? It does it in terms of that last term that was left over. Let me go back and write down the solution. Because here was our solution before. We said there was a resistive force that was proportional, let's just say proportional to the velocity. And we got the solution right here. So there was an initial velocity to the object. It was then acted upon by this force F. There are two terms in there. First, the steady state term, the velocity that is approached asymptotically by the sailboat or whatever is coasting, and then this transient term, which is decaying away. Right. What we're going to consider here in a coasting problem is that this force is 0. So this F is 0. Okay, that means this term is out, and this term is out, and all we're left with is right here. V equals V naught times the decaying exponential. This velocity is decaying to 0 as expected. But it doesn't, the object doesn't stop immediately. Instead, this decaying exponential is what drives it to 0. Notice that you have a bigger resistive force, it will decay to 0 faster. In these coasting problems, you generally like to figure out how far the object goes before it stops, or essentially stops. Right. So before we had that the velocity was v0 e to the minus k over mt. But velocity is a time rate of change of position. So now we have another differential equation. Actually, we can just integrate this. And when we integrate, we find, again, it's a similar integration. It's not hard to do. All you're doing is integrating this exponential. V naught times negative m over k e to a decaying exponential plus some constant integration c. If the initial position of the object is s0, we can use that to evaluate c and find that c is equal to s naught plus m v naught over k. And that's what we're seeing right here. This is c. So this is the expression for the position of the object that starts at s naught. When we start, the force stops on it. It just has a velocity of v naught and s naught when we start calculating this coasting problem. Well, a lot of times you don't know exactly where it is, but you can subtract s naught from s. So we've got s minus s naught. That will give the distance traveled. And I'll write that out on the next slide. And here is the expression for the distance traveled for an object that started coasting at, let me get the pen here. At t equals 0, it had some velocity, v0, and was at some position s naught, but we really don't care what that position is. Here we're just subtracting it, so we'll only get the distance traveled. But we do need to know the initial velocity. And this decaying exponential gives us, as we evaluate this, actually it's a discrete function, as we evaluate this, we find the distance that's traveled by the coasting object. This would be a boat that's coasting with no wind, and it loses power from its motors, scary thing. It could be a hockey puck traveling over ice in which the actual friction, the constant of proportionality, is very, very small. Okay, so here we've, in this lecture, we worked out several differential equations in which we took into account resistive forces when we looked at the equations of motion of an object. In the first case, to find terminal velocity, we looked at how the object obeys when it's subject to gravity and the force of the air resistance. Then we looked at a sailboat in which the force was, the driving force was the wind, and we have the resistive force of the water. And in the third case, we looked at an object that starts with some velocity v0 and suddenly has no forces on it, and we watch how long or how far it travels as it coasts.